Hello, friends. Welcome back. Or, if this is the first time you found your way here, welcome. I'm so glad you're here tonight. Right now, at this very moment, something is holding you. Not a pair of arms, not a chair, not a bed, not even the ground beneath you, not entirely. Something far older, far quieter, far more patient than any of those things is pressing against every cell in your body, drawing you gently, persistently toward the center of the earth. You've felt it your entire life. You've never once seen it. And most of us, if we're honest, have never really stopped to wonder what it actually is. That invisible thing is gravity. And tonight we're going to follow it from the palm of your hand all the way to the edge of the universe. Before we begin this journey together, if these quiet science stories bring you comfort at the end of a long day, you might like to stay a while. You can gently tap the like button, and if you'd like more nights like this, subscribe and ring the little bell not for noise, but so the next quiet story can find its way back to you. Now, let's drift. There's a small experiment you can do right now without moving from where you are. Take any object near you, a book, a phone, a glass of water. Hold it out, then let go. You already know what happens. It falls. Every single time. Always down, always without hesitation. No thinking, no deciding, no delay. The object simply goes. As if it was always meant to. As if down were the only direction that ever mattered. We've watched things fall our entire lives. Children watch things fall before they learn to speak. Civilizations rose and collapsed while things kept falling. Empires were built, languages were born and died, entire species came and went, and through all of it, objects kept dropping toward the earth with the same quiet certainty they have right now tonight as you listen to this. There is something almost meditative about that, something almost sacred. But here's what's strange, and this is the thing most people never pause to notice. Gravity doesn't make a sound. It doesn't flash. It doesn't announce itself. You can't bottle. It can't hold it in your hand, can't point to it the way you'd point to a river or a flame. And yet it is without question the most consequential force in the entire history of the cosmos. Everything you've ever seen, everyone you've ever loved, every mountain and ocean and storm and star, all of it exists because of gravity. All of it was shaped by gravity. And all of it in time will be decided by gravity. So, what is it really? Here's where it gets quietly astonishing. Gravity at its most basic is not a push, it's a pull. Every object in the universe that has mass, every atom, every grain of sand, every planet, every star, pulls on every other object with mass. Right now you are gravitationally attracting the moon. Faintly, almost incomprehensibly faintly, but you are. The moon is pulling back. So is every star you've ever looked at. So is every person in every city on Earth. Everything is pulling on, everything else, always in every direction, all at once, a vast silent web of attraction stretching across the entire universe, never resting, never pausing, never letting go. Scientists describe this with a deceptively simple equation. Isaac Newton in 1687 wrote it down for the first time. The gravitational force between two objects depends on their masses and the distance between them. The more massive the objects, the stronger the pull. The farther apart they are, the weaker it becomes. Double the distance and the force drops to 1/4. Simple on paper, staggering in its implications. Think about what that means for a moment. The sun, sitting 93 million miles away, is still pulling on you right now, as you read this, as you breathe, as you rest. It's pulling on every ocean, bending the path of every satellite, holding every planet in its patient orbit. And the sun itself is being pulled by the center of the Milky Way, a gravitational anchor so massive it takes our entire solar system 230 million years to complete a single orbit around it. We call that a cosmic year. In the entire history of human civilization, every war, every invention, every song ever written, the Earth has moved less than 1/10,000th of the way around the galaxy. Gravity has been quietly steering that journey the whole time. Now, here is something most people get wrong about gravity, and it's a beautiful misconception worth gently correcting. Many of us grow up thinking of gravity as something Earth does, our gravity down here pulling things toward our surface. But gravity isn't a property of planets. It isn't something special about Earth. Gravity is a property of mass itself, of matter existing. You don't need a planet, you don't need a star. Two dust particles floating in the emptiness of space will pull toward each other if given enough time and no other disturbances. Gravity is in that sense the universe's most democratic force. It belongs to everything. It plays no favorites. And yet, and this is one of the quiet paradoxes that makes gravity so endlessly interesting, it is also the weakest of all the fundamental forces. Electromagnetism is vastly stronger. The forces that hold atomic nuclei together are stronger by factors that are almost impossible to put into everyday language. You can demonstrate gravity's weakness with something as small as a refrigerator magnet. A tiny magnet can hold a paperclip against the pull of the entire Earth, the electromagnetic force in that small piece of metal, overpowering the gravitational attraction of a planet 6 septillion kilograms in mass. And yet, gravity wins in the end, always. Because it has one advantage the others don't, it never cancels out. Electric charges can attract and repel positive and negative, balancing each other into silence. Gravity only pulls, it accumulates. And over cosmic time scales with cosmic amounts of mass, that one-sided patient accumulation becomes everything. Have you ever stood at the edge of something high, a cliff, a tall building, a bridge, and felt that strange pull, that quiet, irrational whisper from below? Scientists have actually studied this. It's sometimes called the high place phenomenon, a brief involuntary urge that many people feel near edges even when they have absolutely no intention of jumping. Some researchers suggest it may be the mind misreading the body's signals about danger, a strange loop of awareness turned back on itself. But others have wondered more poetically if there's something deeper in it, if some ancient part of us still registers, however briefly, the raw pull of the earth, not as danger, as presence. Think about the way water moves in your body right now. Think about the way your blood circulates, the way your lungs expand, the way your spine aligns itself when you stand or sit or lie down. All of that is happening in a constant, never-ending negotiation with gravity. Your skeleton is literally shaped by gravity. Bones grow denser where they bear weight, weaker where they don't. Astronauts who spend months on the International Space Station return to Earth with bones measurably less dense than when they left. Their bodies, freed from the steady pull, began quietly assuming they didn't need to be as strong. When they land, they sometimes can't walk immediately. Their muscles have forgotten what it feels like to carry weight. It can take weeks, sometimes months, for a human body to remember how to exist inside gravity's embrace again, which tells you something extraordinary. We are not just living on a planet held together by gravity. We are organisms that were assembled by it, shaped by it, calibrated to it across hundreds of millions of years of evolution. There is a species of tree, the black poplar, whose roots have been found growing nearly 30 feet deep into soft riverbanks. Not toward water, not toward nutrients, but straight down. Researchers studying this behavior suggest that certain plant tissues respond to what biologists call gravitropism, the directional sensing of gravity. Plants know which way is down. They have known without brains, without nerves, without any nervous system at all, which direction the planet is pulling, and they have organized their entire lives around that knowledge. Roots go down, stems go up. Every seed that falls in darkness and sprouts without ever seeing, the light still knows, somehow, which way to reach toward the surface, and which way to anchor into the earth. Gravity taught them that. Gravity has been teaching living things that for billions of years. Here is something to sit with quietly for a moment. The force that keeps you in your chair, that roots the tree outside your window, that holds the atmosphere in place so you have air to breathe, that very same force operating at larger and larger scales built every star in the sky. Every single one. Gravity gathered the raw material, compressed. It heated it, ignited it, and held it together long enough to shine. The same pull that keeps a teacup on a table also over billions of years assembled galaxies. The very same physics, the very same invisible hand. The scale simply changes. The principle never does. And perhaps that is what makes gravity so quietly remarkable. Not its strength, not its reach, though both are staggering, but its consistency. In a universe of constant change of explosions and collapses and birth and death and transformation, gravity is the one thing that behaves exactly the same way it always has. The equation Newton wrote in the 1600s still correctly predicts the path of a spacecraft launched in 2024. The force pulling on you tonight is the same force that pulled on the first living cells in the first ocean. The same force that shaped the first mountains, the same force that drew the first clouds together in the first atmosphere of a young Earth 4.5 billion years ago. Nothing about it has changed. Nothing. There is something almost comforting in that, isn't there? In a world that sometimes feels like it shifts too quickly, gravity remains. Quiet, constant, patient, holding everything just a little closer together. But here's what I want you to hold on to as we move deeper into this story tonight. We have only just arrived at the surface. We've seen gravity in your hand and your bones, in the roots of trees and the orbit of planets. We've heard Newton's elegant summary from 1687, and yet all of it is only the beginning of what gravity actually is. Because in the early 20th century, a young patent clerk in Switzerland began to suspect that Newton, brilliant as he was, had only told half the story. That gravity wasn't just a force reaching between objects, that it was something stranger, something deeper, something woven into the very fabric of space and time itself. And the moment that idea was confirmed with light bending around the sun, measured during a solar eclipse in 1919, physics would never be the same again. But before we reach that revelation, we need to understand how humanity got here, how centuries of brilliant minds looked at falling objects and got it wonderfully confidently wrong, and what it finally took to see clearly. For nearly 2,000 years, the smartest people on Earth looked at falling objects and drew the wrong conclusion, not because they were careless, not because they weren't paying attention, but because the wrong answer felt so completely obviously right that almost no one thought to question it. That is where this part of the story begins, not with a discovery, but with a mistake. A beautiful, confident, remarkably stubborn mistake. Picture Athens around 350 BCE. A man named Aristotle, one of the most brilliant minds the ancient world ever produced. A person who wrote with authority on biology, ethics, politics, poetry, logic, and the nature of the cosmos, is watching objects fall. He observes, he thinks, and he concludes with total confidence that heavier objects fall faster than lighter ones. A stone falls faster than a feather. A boulder falls faster than a pebble. It seems obvious. It seems self-evident. It seems like the kind of thing you don't even need to test because anyone with eyes can see it. And for roughly 19 centuries, almost no one pushed back. Think about that for a moment. 19 centuries. Generation after generation of educated, thoughtful people accepted this claim without serious challenge. It was copied into texts taught in universities, repeated by scholars across Europe and the Arab world and Persia. Not because everyone was gullible, but because Aristotle's conclusion matched everyday experience well enough that the error stayed invisible. You drop a heavy rock and a dry leaf at the same time the rock hits the ground first. Every time. The conclusion seems to write itself. But here's what Aristotle missed, and what almost everyone missed for nearly 2 millennia after him. The leaf doesn't fall slowly because it's light. It falls slowly because of air resistance. Remove the air and the leaf and the rock fall at exactly the same rate. Aristotle wasn't wrong about what he observed. He was wrong about what was causing it. This is one of the most important lessons in the history of science, and it's worth sitting with quietly. Observation and explanation are two entirely different things. You can see something perfectly clearly and still misunderstand it completely. The data and the story you tell about the data are not the same thing. And the story, if it goes unchallenged long enough, can become so embedded in human thinking that even brilliant people stop noticing it's a story at all. Now, most people who know anything about this history will immediately think of one name, Galileo. And there's a famous story, you may have heard it, of Galileo climbing to the top of the Leaning Tower of Pisa, dropping two cannonballs of different weights simultaneously and watching them hit the ground, at the same time disproving Aristotle in front of a crowd of stunned onlookers. It's a wonderful story. It has drama precision, a clear villain, and a clear hero. There is only one problem with it. It almost certainly didn't happen. Historians who have studied Galileo's actual writings and correspondence have found no credible account of the Tower of Pisa experiment. It appears in one biography, written by a student decades after the fact, likely embellished or entirely invented. What Galileo actually did was both more careful and less theatrical, and in some ways more interesting. What Galileo truly pioneered in the late 1500s and early 1600s was something we now call experimental method. Rather than watching objects fall freely, which happened too fast to measure accurately with the tools he had, he cleverly slowed gravity down. He built carefully inclined planes, essentially long ramps of polished wood, with grooves cut into them, and rolled bronze balls down them at different angles. By tilting the ramp at a shallow angle, he could slow the ball's descent enough to time it with a water clock, a device that measured elapsed time by the volume of water that dripped through a hole. And what he found every time, regardless of the ball's weight, was the same mathematical relationship: the distance traveled increased not in proportion to time, but in proportion to time squared. A ball rolling for 2 seconds had traveled 4 times as far as after 1 second. 3 seconds, 9 times as far. The pattern was elegant, precise, and utterly independent of the ball's mass. Galileo didn't just disprove Aristotle. He replaced a vague observation with a mathematical law. He turned things fall into something you could calculate, predict, and verify. That shift from description to equation is one of the most consequential moves in the history of human knowledge. But here's something that often gets lost in the celebration of Galileo. He described how things fall. He could tell you exactly where a falling object would be at any moment in time. What he couldn't tell you, what he freely admitted he couldn't tell you, was why. What was actually causing the acceleration? What was the invisible thing pulling objects toward the Earth? Galileo observed the pattern. He didn't have an explanation for the pattern. That gap, that unanswered why, would remain open for decades after his death in 1642. The person who would fill it was born that same year. Isaac Newton's early life does not read like the biography of a revolutionary. He was a premature baby, small enough at birth that his mother later said he could have fit inside a quart pot. His father died before he was born. He had a difficult childhood, was sent to live with his grandmother for years, while his mother remarried and by some accounts was not a particularly remarkable student in his early years. What changed him? What opened something in his mind seems to have been a period of enforced solitude. In 1665 and 1666, the University of Cambridge, where Newton was a young scholar, was shut down because of a devastating outbreak of plague. Newton returned to his family home in Woolsthorpe, a small village in Lincolnshire, with nothing but time and his own thoughts. And in those roughly 18 months sitting in a farmhouse largely isolated from the academic world, he effectively invented calculus, made foundational discoveries in optics, and began developing the theory of universal gravitation. Now, about that apple. Did an apple fall near Newton and inspire him to think about gravity? Possibly. Newton himself told the story in old age, and a few people who knew him recorded versions of it. There was indeed an apple tree at Woolsthorpe Manor, and a descendant of that tree still grows there today. But the popular image apple bonks Newton on the head, Newton invents gravity as a Hollywood simplification of something far more subtle and interesting. What the Apple story in its most plausible version actually represents is a moment of genuine conceptual leap. Newton looking at a falling apple and asking not, why does it fall in the simple everyday sense, but does the same force that pulls this apple also pull the moon? That question is everything. Because if the force acting on a small apple near the Earth's surface is the same force simply diminished by distance that keeps the moon in its orbit, then gravity is not a local phenomenon. It is universal. It reaches everywhere. It never stops. To test this idea, Newton did something elegant. He calculated how fast the moon would need to be accelerating toward Earth to stay in its orbit rather than flying off into space. Then he calculated what his proposed inverse square law, the idea that gravity weakens with the square of distance, would predict for an object as far away as the moon. The two numbers agreed, not approximately, precisely. The moon was, in effect, falling toward Earth continuously, but moving forward fast enough that it kept missing. Every orbit is, in a sense, an endless fall that always curves past the horizon. Here is an image worth holding in your mind for a moment. Imagine standing on top of an impossibly tall mountain and throwing a ball horizontally. Throw it slowly, and it curves down to the ground quickly. Throw it faster, and it travels farther before landing. Throw it fast enough, roughly 17,500 miles per hour at Earth's surface, and the curve of its fall perfectly matches the curve of the Earth's surface. It falls continuously, but the ground curves away beneath it at exactly the same rate. It is now orbiting. The International Space Station is doing exactly this every 90 minutes at roughly 250 miles above your head. It is not being held up. It is falling perpetually beautifully in a circle. Gravity is doing everything. The station just has enough sideways speed to keep missing the planet. Does it change something in you just slightly to think of orbiting not as floating above gravity, but as falling through it endlessly? There's a kind of poetry in that, a kind of humility. Newton published his theory of universal gravitation in 1687 in a work called The Principia Mathematica, widely considered one of the most important scientific texts ever written. With a handful of equations, he explained the motion of falling apples, artillery shells, ocean tides, the orbits of planets, and the trajectories of comets. For more than 2 centuries, his framework was simply the truth. Engineers used it to build bridges. Astronomers used it to predict the positions of planets with extraordinary accuracy. In 1846, astronomers used Newton's equations to deduce the existence of the planet Neptune, a world no human eye had ever seen purely from the slight wobble its gravity was causing in the orbit of Uranus. They pointed a telescope exactly where the math said the unseen planet should be. It was there. Newton's gravity applied with careful arithmetic had found a hidden world. That moment, a planet discovered by mathematics alone, remains one of the most breathtaking achievements in the history of science. And it is worth asking how many other things might be found that way. How many truths about the universe are already written in equations, waiting for someone patient enough to follow them to their conclusion? But Newton himself, for all his genius, was uncomfortable with one aspect of his own theory. He could describe gravity perfectly. He could calculate its effects with astonishing precision. What he could not do, what he explicitly refused to speculate about, was explain what gravity actually was. How did the sun reach across 93 million miles of empty space and pull on the Earth? Was that pull instantaneous? Did it require some medium to travel through? Newton wrote famously, "I feign no hypotheses," by which he meant, I'm not going to invent explanations I can't test. The math works. The predictions are accurate. What gravity is in some deeper physical sense, I do not know. It was an act of remarkable intellectual honesty. And it left a door open, a quiet, unresolved question sitting at the foundation of the most successful physical theory in history that would remain ajar for more than 200 years, until a young man in a patent office in Bern began to wonder whether space itself was something that could bend. But that revolution comes later. First, let's follow gravity to where it truly shows its creative power, not in the fall of an apple, not in the orbit of a moon, but in the birth of something so hot and so bright it can be seen across 1 billion light years of empty space. Somewhere in our galaxy right now, in a region of space so cold, it makes Antarctica feel warm, a star is being born, not in fire, not in explosion, in silence. In the slow, patient gathering of gas so thin that a cubic foot of it contains fewer molecules than the best vacuum humans have ever created in a laboratory. And yet, from that near-nothingness gravity is quietly assembling something that will burn for 10 billion years. The story of how stars are made is at its heart a story about patience, about what happens when a force as gentle as a whisper is given enough time and enough material to work with. And by the end of this part of our journey, I think you'll find it nearly impossible to look up at the night sky the same way again. Let's begin with the raw material. Between the stars and the spaces we tend to think of as empty. The universe is filled with vast clouds of gas and dust, mostly hydrogen, some helium, traces of heavier elements leftovers from stars that lived and died long before our sun existed. Astronomers call these clouds nebulae, from the Latin word for mist or cloud. And some of them are so enormous that the distance from one edge to the other would take light itself hundreds of years to cross. The Orion Molecular Cloud, which sits roughly 1,300 light-years from Earth and is one of the most active star-forming regions near our solar system, contains enough raw material to assemble tens of thousands of stars the size of our sun. For most of its existence, a molecular cloud just drifts. Cold, slow, thinly spread. But something can disturb it. Maybe a nearby star explodes in a supernova, a shock wave rippling outward through space, compressing the cloud slightly as it passes. Maybe two clouds drift into each other, their edges merging and thickening. Maybe the slow rotation of the galaxy itself creates density waves that sweep through the gas like ripples through water. Whatever the trigger, what happens next is always the same. In one region of the cloud, the gas becomes slightly denser than the surrounding material, and that slight density, that barely their concentration, exerts a slightly stronger gravitational pull on its neighbors. More gas is drawn in. The density increases. The gravitational pull increases. More gas arrives. The cloud begins to collapse toward that point slowly at first, then faster and faster, in a process astronomers call gravitational collapse. Here is where a common misconception deserves some attention. Many people imagine that stars simply condense smoothly from a cloud into a ball, the way a raindrop might form from water vapor. But the actual process is far more turbulent, far more dramatic, and involves a series of competing forces that make it something of a miracle that stars form at all. As the gas cloud collapses, it doesn't just fall inward quietly. It also spins. And as it spins faster, the same way a figure skater spins faster, when they pull their arms in, the cloud flattens into a disk. Most of the mass falls toward the center, forming what astronomers call a protostar. The rest of the material orbits around it in a swirling disk that will eventually, over millions of years, become planets. But we'll follow that thread in the next part of our story. For now, all attention is on what's happening at the center. The protostar is not yet a star. It is a dense hot knot of gas, still collapsing, still gathering mass, still heating up, as gravitational energy is converted into thermal energy. At this stage, it is completely invisible from the outside, buried under layers of infalling gas and dust, so thick that even powerful telescopes cannot see through them in visible light. Only infrared and radio telescopes, which detect different wavelengths of radiation, can peer into these stellar nurseries and show us what's happening inside. And what they show is chaos, turbulent flows of gas, shock waves, jets of material being ejected from the poles of the collapsing protostar at hundreds of miles per second. It is in every sense a construction site, and construction sites are rarely quiet or clean. But what transforms a protostar into a true star? What crosses the threshold between a hot, collapsing ball of gas and a genuine nuclear furnace is one of the most dramatic moments in astrophysics. As the core of the protostar contracts, the gas at the center is compressed to extraordinary densities. The temperature climbs, hundreds of thousands of degrees, then millions. And at approximately 10 million degrees Celsius, a number so large it barely has meaning in everyday life, something switches on. Hydrogen nuclei, which are single protons, are now moving fast enough and are packed tightly enough that they begin to collide and fuse. Two protons merge, then two more, then the products combine, releasing a burst of energy in the process. This is nuclear fusion, the same process that powers a hydrogen bomb, but happening continuously steadily at the core of what is now for the first time a star. And here is the most important thing to understand about a star. The thing that most textbooks mention but rarely linger on long enough, a star is not simply burning. A star is a battlefield. From the moment nuclear fusion ignites, two forces are locked in permanent opposition at every point inside the star's body. Gravity pulls every layer of gas inward toward the center, with the same patient insistence it always has. And the energy released by nuclear fusion pushes outward as radiation pressure, as heat, as the sheer momentum of photons streaming away from the core. For as long as the star lives, these two forces are perfectly balanced. The inward pull of gravity exactly equals the outward push of fusion energy. Astronomers call this balance hydrostatic equilibrium. Every moment of a star's life is in a sense a drawn battle between collapse and explosion. The star is simultaneously trying to crush itself and blow itself apart, and for billions of years, neither side wins. It's worth asking yourself, have you ever thought about the sun that way? Not as a distant steady lamp in the sky, but as a site of constant violent negotiation. The warmth on your skin on a clear afternoon is the light that escaped that battle. Photons generated at the sun's core bouncing and scattering through layers of dense plasma for tens of thousands of years, before finally reaching the surface and flying across 93 million miles of space to touch your face. Some of the light warming you right now began its journey inside the sun before the first humans walked the Earth. The mass of a star at birth determines almost everything about its life: its brightness, its color, its temperature, and most crucially, how long it will live. And here the relationship is counterintuitive in a way that often surprises people. Bigger stars do not live longer. They live dramatically shorter lives. A star with 10 times the mass of our sun burns its fuel roughly 10,000 times faster. While our sun will spend roughly 10 billion years on the main sequence, the stable hydrogen fusing phase of stellar life, a massive star of 30 solar masses might exhaust its fuel in just a few million years. In cosmic time, that is barely a breath. These brief, brilliant giants burn with a blue-white ferocity outshining the sun by factors of tens of thousands, and then they die spectacularly in supernovae, so bright they can outshine entire galaxies for weeks. Our sun, by contrast, is a middle-aged medium-mass yellow dwarf star, modest by stellar standards, unremarkable in almost every measurable way. And yet, its very mediocrity is, from our perspective, a profound gift. Its 10 billion year lifespan gave the chemistry of life enough time to slowly, tentatively, improbably unfold on a small rocky planet in its habitable zone. Had our sun been twice as massive, it would have burned out billions of years before complex life had any chance to emerge. Had it been smaller and cooler, its habitable zone might have been so close that tidal forces would have locked any nearby planet in permanent day and night. The sun's ordinariness, it turns out, is exactly what we needed. Now here is something that sits quietly at the edge of wonder. Every atom of oxygen in your lungs right now was forged inside a star. Not our sun. Our sun is still burning through its hydrogen and has not yet reached the stage where it creates oxygen. The oxygen in your body was made in a star that died long before our solar system existed, scattered into space by a supernova drifting through a molecular cloud for millions of years, eventually incorporated into the disk of gas and dust that condensed into the sun, the earth, and you, the calcium in your bones, the iron in your blood, the carbon that forms the backbone of every molecule in your cells. All of it was assembled in the nuclear furnace of a star, expelled in that star's death, and recycled into the world you inhabit. You are, in the most literal and chemically verifiable sense, made of stardust, not as a metaphor, as a fact. The astronomer Carl Sagan said it first, and perhaps most memorably. But the science behind that phrase, "we are made of star stuff," is not poetic license. It is nuclear astrophysics. Every element heavier than hydrogen and most helium was created inside a star, or in the violent collision of dead stars. The universe began with hydrogen. Stars turned hydrogen into everything else. And gravity is what built the furnaces. There's a particular star-forming region that researchers studying the Hubble Space Telescope's images have returned to again and again, the Eagle Nebula, about 7,000 light-years from Earth home, to the famous structures known as the Pillars of Creation. Those pillars made of gas and dust are places where new stars are actively being born. The dense tips of the pillars resist the erosive radiation from nearby massive stars long enough for gravity to do its slow work inside collapsing pockets of gas into protostars that will one day shine on their own. The pillars themselves are being slowly destroyed by the very stars they helped create. There is something quietly moving about that. The parent consumed by the child. The cloud giving itself entirely to the light. What scientists now suspect based on observations of hundreds of star-forming regions across the galaxy is that most stars, perhaps the vast majority, do not form in isolation. They form in clusters, dozens or hundreds or thousands of stars, condensing from the same molecular cloud over a span of a few million years, then gradually dispersing over time as the cluster ages and individual stars drift apart under the gentle gravitational nudges of the galaxy. Our own sun almost certainly formed in such a cluster roughly 4.5 billion years ago. Its siblings, the stars that were born from the same molecular cloud at roughly the same time, are now scattered across the Milky Way, so widely separated that we may never be able to identify them with certainty. The sun grew up in a family. It has been drifting alone through the galaxy for billions of years. Is there something in that image that feels quietly recognizable? Gravity built the sun from a cloud of cold gas. Gravity is building new stars right now and nebulae scattered across the Milky Way, and in galaxies 100 million light-years away. And that same gravity, the same force working in the same way, was simultaneously doing something else in the disk of material surrounding each new star. Something smaller in scale, but no less extraordinary. It was building worlds. 4.5 billion years ago, there was no Earth. There was no moon. There was no ground beneath anyone's feet, no ocean, no sky, no morning, no night. There was only a young star, our sun newly ignited, and surrounding it a vast flat, slowly spinning disk of gas and dust. From the outside, if anything had been there to observe it, it would have looked almost peaceful, almost unremarkable. Just a disk, just debris. And yet inside that disk, gravity was already at work doing something that would eventually produce every mountain range, every ocean trench, every living cell on Earth. It was building a world from scratch, grain by grain, collision by collision, over millions of years of patient, unhurried accumulation. The story of how planets form is one of the most layered, surprising, and when you follow it all the way through, personally significant stories in all of science. Because it ends with you. It ends with this moment right now wherever you are. Let's trace it from the very beginning. In the disk surrounding the young sun, the material was not evenly distributed. Temperature played a crucial role in sorting it. Close to the sun, where temperatures were high, only materials with very high melting points could exist in solid form: rocky minerals, metals, silicates. Volatile materials like water ice, methane, and ammonia could only remain solid far from the sun's heat, beyond a boundary that planetary scientists call the frost line or snow line. This invisible boundary sits roughly where the asteroid belt is today, between the orbits of Mars and Jupiter. Inside the frost line rocky material. Outside, ice and gas in abundance. That single thermal gradient set by the young sun's warmth determined the basic character of every planet in our solar system before a single planet had yet formed. Now, the process begins in the quietest possible way. Dust particles, microscopic grains of silicate minerals, and carbon compounds smaller than the particles in cigarette smoke collide gently in the disk and sometimes stick together. Not always. Sometimes they bounce apart. Sometimes they shatter. But often enough they adhere, forming loose aggregates that grow slowly over thousands of years, from specks to pebbles, from pebbles to rocks, from rocks to boulders. At some point, and this is a stage that planetary scientists are still actively working to understand in detail, these larger bodies, now perhaps kilometers across, reach a size where their own gravity begins to matter. And at that point, everything changes. Once a growing body becomes massive enough to have meaningful gravitational pull, it stops relying on random collisions to grow. It begins actively attracting material. Nearby rocks and boulders are drawn toward it. Smaller bodies that pass close enough are captured. Collisions become more frequent and more energetic. The body grows faster as it grows larger, its gravity strengthening as its mass increases, drawing in ever more material from ever greater distances. Planetary scientists call these growing bodies planetesimals, and eventually the largest of them, the ones that happen to be in the right place, with the right starting mass, with the right neighbors, become planetary embryos, objects the size of our moon or Mars, already hundreds or thousands of kilometers across. At this stage, the inner solar system was a place of extraordinary violence. Dozens of planetary embryos, each massive enough to generate real gravity, were crossing each other's orbits, colliding, merging, sometimes shattering, slowly, sorting themselves out through a process of gravitational competition that lasted tens of millions of years. The Earth you stand on is the survivor of that competition. It grew by consuming smaller bodies, absorbing their mass, adding their material to its own, growing denser and hotter with each collision as the kinetic energy of impact was converted to heat. The early Earth was not solid rock. It was a magma ocean, a globe of churning molten rock, glowing red and orange with no crust, no ocean, no atmosphere worth speaking of. It looked nothing like home. And then came the impact that changed everything. Roughly 5 billion years ago, scientists believe within the first 100 million years of the solar system's history, a body roughly the size of Mars, which planetary scientists have named Theia, was on a collision course with the young Earth. The two worlds had been growing in similar orbits, and their gravitational relationship had become unstable. The impact when it came was not a gentle nudge. It was a collision at perhaps 15,000 miles per hour between two bodies, each containing billions of cubic kilometers of rock and metal. The energy released was incomprehensible. Much of Theia's iron core merged with Earth's. An enormous quantity of rocky material from both bodies' mantles was blasted into space, and that orbiting cloud of debris, still hot, still glowing, began to coalesce under its own gravity into a new body. Within perhaps 1,000 years, an eye blink in geological time, the moon had formed. This giant impact hypothesis, as it's known, explains several features of the moon that had puzzled scientists for decades. The moon has a relatively small iron core compared to its size, consistent with being assembled, mostly from mantle material rather than core material. The moon's chemical composition is strikingly similar to Earth's mantle in many ways, yet distinct in others, consistent with a mixture of Earth material and Theia material. The moon is also unusually large relative to its host planet. Our moon-to-Earth ratio is the highest in the solar system for a rocky planet. And the event explains why Earth has an axial tilt of about 23.5 degrees. That collision almost certainly altered Earth's rotation. Without that tilt, Earth would have no seasons. Without seasons, the climate patterns, ocean circulation, and ecological variety that shape the conditions for complex life might never have developed. The moon was not an accident. It was a consequence of gravity, of orbital dynamics, of the violence inherent in planetary formation, of the way gravity draws bodies together until something decisive happens. And the moon's presence in turn has shaped almost everything about life on Earth, as we'll follow more closely in just a moment. Now, let's return to the frost line, that invisible thermal boundary, and explore the other half of the solar system. Beyond it, the story of planet formation played out very differently. In the outer solar system, planetary embryos were forming the same way through accretion, through collisions, through gravitational competition. But out there beyond the frost line, there was far more raw material available. Water, ice, methane, ice, ammonia, all the volatile compounds that couldn't exist as solids in the inner solar system were present in enormous abundance in the outer disk. The embryos that formed beyond the frost line grew large quickly because there was so much to gather. And once they reached a critical mass, somewhere around 10 Earth masses, researchers suggest something remarkable happened. Their gravity became strong enough to capture not just solid material, but gas directly from the disk. Hydrogen and helium, the lightest and most abundant elements in the solar system, began raining down onto these growing worlds. Jupiter is the most dramatic result of this process. It likely reached its critical mass within the first few million years of the solar system's history, possibly before the disk had fully formed, and then spent the next few million years accreting hydrogen and helium at a staggering rate. Today, Jupiter contains more than twice the mass of all the other planets in the solar system combined. Its gravitational influence is so dominant that it has shaped the architecture of the entire solar system, scattering smaller bodies, preventing the asteroid belt from ever coalescing into a full planet, redirecting comets, and quite possibly playing a role in delivering water to the early Earth. By nudging icy bodies from the outer solar system inward, there is an active and genuinely fascinating debate among planetary scientists about whether Jupiter has been on balance a protector of life on Earth or a threat to it. The traditional view, sometimes called the Jupiter shield hypothesis, holds that Jupiter's gravity acts as a gravitational vacuum cleaner, capturing or ejecting many of the comets and asteroids that would otherwise repeatedly devastate the inner solar system. Without Jupiter, so this argument goes, Earth would be pummeled by large impactors, far more frequently making the development of complex life extremely difficult. Some researchers, however, have pushed back on this view, suggesting that Jupiter may actually have delivered as many dangerous impactors to the inner solar system as it deflected. The debate is ongoing. What is not in question is that Jupiter's gravity is a dominant presence in our cosmic neighborhood, shaping the fates of smaller bodies in ways we are still working to fully understand. Here is something worth pausing on for a moment. We tend to think of Earth as the default, the standard rocky planet, the reference point. But Earth's particular combination of features is, as far as we currently know, extraordinarily rare. The right size so that gravity is strong enough to hold a substantial atmosphere, but not so strong it retains thick hydrogen that would smother chemistry. The right distance from the sun inside the habitable zone, where liquid water can exist on the surface. The right amount of water enough to fill the oceans, but not so much that the entire surface is submerged and plate tectonics impossible. A large moon stabilizing its axial tilt. A protective giant planet in the outer solar system. A magnetic field generated by its liquid iron core shielding the surface from the solar wind. Every one of those features traces back in one way or another to gravity. The right mass came from gravitational accretion. The right distance came from where, in the gravitational sorting of the early solar system, Earth's embryo happened to form. The moon came from a gravitational collision. The magnetic field exists because gravity compressed the Earth's interior hot enough to keep its iron core liquid. Even the plate tectonics that recycle carbon and regulate temperature over geological timescales are at their root, driven by the heat generated during Earth's gravitational formation and subsequent impacts. Gravity did not just build the Earth. Gravity built the Earth to be habitable. Not intentionally, there is no intention in physics, but the same force that collapses gas clouds into stars, the same force that draws pebbles together into boulders produced by way of billions of years of accumulation and collision and sorting a world with liquid water and breathable air and stable seasons and a protective sky. Have you ever stood outside on a clear night and looked up and felt small, and then a moment later felt somehow held? Like the universe was not indifferent exactly, but paying a kind of quiet attention. The science doesn't promise meaning, but it does tell us this. The conditions that allow you to stand there and feel that feeling were assembled over 4.5 billion years by the same force that holds everything together. Gravity built the stage. Life walked out onto it. But all of this, the stars, the planets, the conditions for life, depends on something that we've been circling around and haven't yet examined directly. The architecture of orbits. The reason planets don't just fall into their stars. The reason moons stay close without crashing down. The reason the solar system has been stable enough, long enough for life to unfold at all. And woven through all of that is one of the most surprising gifts gravity has ever given the Earth, a gift delivered every single day on every coastline in the world, twice a day, like clockwork. And yet, almost no one thinks about where it truly comes from. Every night without fail, the ocean pulls back from the shore and then returns. Fishermen have read this rhythm for thousands of years. Ancient civilizations built calendars around it. Sailors trusted their lives to it. And yet, for most of human history, the true cause of the tides was one of the most persistently misunderstood phenomena in all of natural science. Even some of the greatest minds in history got it wrong, spectacularly confidently wrong, in ways that tell us something important about how difficult it is to see the full shape of a force you cannot directly observe. Galileo, the same man who revolutionized our understanding of falling objects, believed that tides were caused by the sloshing of water as the Earth rotated and orbited the sun, essentially, that the ocean was being shaken like water in a moving bucket. He was so convinced of this explanation that he used it as an argument in favor of the Earth's motion around the sun. He was wrong. The tides are not caused by Earth's motion alone. They are caused by the moon's gravity, and by something subtler and more interesting than a simple pull. Let's untangle this carefully because the real explanation is far more beautiful than most people ever learn. When we say the moon pulls on the Earth, we tend to picture a simple tug, the moon on one side pulling the whole Earth toward it. But gravity doesn't work on the Earth as if it were a single point. It works on every part of the Earth separately, and crucially, it works with different strengths at different distances. The side of the Earth facing the moon is roughly 4,000 miles closer to the moon than the center of the Earth. The side facing away is 4,000 miles farther. Because gravity weakens with distance, the near side feels a stronger pull than the center, and the center feels a stronger pull than the far side. These differences in gravitational strength, what scientists call tidal forces, are what stretch the Earth along the Earth-Moon axis. The oceans on the near side are pulled slightly toward the moon bulging outward, and the oceans on the far side here is the part that surprises nearly everyone also bulge outward away from the moon, because they are being pulled less strongly than the Earth's center, and are effectively left behind as the Earth is tugged forward. Two tidal bulges, one facing the moon, one facing directly away. As the Earth rotates through these bulges every 24 hours, most coastlines experience 2 high tides and 2 low tides per day. Not because the moon is directly overhead twice, it isn't, but because you pass through both bulges as the Earth spins. The moon doesn't slosh the ocean, it stretches it. And the Earth rotates through that stretched shape like a ball spinning inside a slightly elongated sleeve of water. Now, here is where the story deepens into something genuinely astonishing. The tidal bulge on the side of the Earth facing the moon does not sit perfectly aligned with the moon. Because the Earth rotates faster than the moon orbits, the Earth completes a full rotation in 24 hours, while the moon takes about 29 days to orbit. The tidal bulge is always being dragged slightly ahead of the moon by Earth's rotation. The bulge leads the moon by a small angle, and that displaced bulge, being a concentration of mass, exerts its own gravitational pull backward on the Earth's rotation, slowing it down, and forward on the moon, gradually accelerating it in its orbit. The consequence of that subtle, persistent gravitational tug is one of the most profound slow motion processes happening in our solar system right now. The moon is gradually spiraling outward. Every year, the moon moves approximately 3.8 centimeters farther from Earth. We know this not from calculation alone, but from direct measurement laser reflectors left on the moon's surface by Apollo astronauts in 1969 allow scientists to bounce laser pulses off them and measure the moon's distance to within millimeters. 4 billion years ago, the moon was dramatically closer, perhaps only a third of its current distance filling a far larger portion of the sky. The tides it raised on early Earth were correspondingly enormous, perhaps hundreds of feet high, sweeping across shallow coastal regions with a force that shaped the early geology of continents. And Earth was rotating faster. Then a day on early Earth may have been only 6 hours long, meaning the planet completed 4 full rotations for everyone it completes today. All of that has changed because of tides. The moon's gravity has been steadily breaking Earth's rotation for billions of years, and the rotational energy being lost by the Earth is being transferred through that displaced tidal bulge into the moon's orbit. Earth slows, moon moves outward. The total energy of the system is conserved. The dance simply evolves. Have you ever seen a total solar eclipse? That extraordinary once-in-a-lifetime experience where the moon fits so precisely over the sun's disk that the sun's corona, its outermost atmosphere, becomes visible as a shimmering halo around a black circle. That perfect fit, which has inspired awe and terror in human beings throughout history, is a coincidence of the present moment in cosmic time. The sun's diameter is about 400 times larger than the moon's. The sun is also about 400 times farther away. These two facts cancel each other out almost perfectly, making the moon and the sun appear nearly identical in size from Earth's surface. But because the moon is slowly moving away from Earth, total solar eclipses are a temporary phenomenon. Hundreds of millions of years from now, the moon will be too far away to cover the sun completely. Future observers, if any exist, will only ever see annular eclipses, where the moon leaves a ring of sunlight visible around its edge. The perfect eclipses that have defined human wonder for millennia are already in a cosmic sense beginning to end. This is the moon's orbit. But to truly understand orbits, why anything stays in orbit, why planets don't spiral into the sun, why the solar system has remained stable long enough for us to be here, we need to go back to a thought experiment that Newton described in the Principia, one of the most clarifying images in the history of physics. Imagine a cannon placed on top of a mountain so tall that its peak is above the atmosphere, no air, no drag. Fire a cannonball horizontally. It travels forward and curves downward, striking the ground some distance away. Fire it faster. It travels farther before curving down. Fire it faster still. At some velocity, the cannonball travels so fast that as it curves downward, the Earth's surface curves away beneath it at exactly the same rate. The cannonball never gets closer to the ground. It is orbiting. It is falling continuously, always accelerating toward Earth, but always moving forward fast enough to miss. An orbit is not an escape from gravity. An orbit is gravity channeled into a circle by sideways motion. This is the conceptual key that unlocks everything. The moon is falling toward Earth. Earth is falling toward the sun. The Milky Way's stars are falling around the galactic center. Every orbit in the universe is a perpetual fall redirected into a curve by the combination of gravity's pull and the orbiting body's sideways momentum. Remove the sideways momentum, and the body falls straight in. Remove the gravity, and the body flies off in a straight line. The orbit is the balance point between those two outcomes, and in a universe with no air resistance, no friction in space, that balance point can persist essentially forever. But orbits in the real solar system are not perfectly simple circles. They are ellipses, slightly oval paths, and they are subject to gravitational nudges from other bodies. Jupiter's gravity perturbs the orbits of asteroids. The moon perturbs Earth's orbit ever so slightly. Venus and Mars pull on Earth with measurable if small gravitational effects. Over time scales of tens of thousands of years, these accumulated nudges cause Earth's orbit to stretch and compress its axial tilt, to wobble slightly its orientation in space, to shift in a slow wobble called precession. Together, these variations are known as Milankovitch cycles, named after the Serbian mathematician Milutin Milankovitch, who calculated them in the early 20th century. And researchers now believe that Milankovitch cycles have been the primary pacemaker of Earth's ice ages, driving the advance and retreat of continental glaciers over hundreds of thousands of years by subtly changing how much sunlight reaches different latitudes at different times of year. Think about that for a moment. The ice ages that sculpted the Great Lakes, carved the valleys of the Alps, drove human migration across continents, and shaped the genetic history of our species. All of it choreographed at the deepest level by the gravitational interactions of planets. Jupiter nudges an asteroid. That changes Earth's orbital shape by a fraction of a percent. Over 40,000 years, that fraction reshapes the climate. The glaciers advance. The species that can't adapt disappear. The ones that can survive. And among the survivors, intelligence becomes an advantage. There is a line improbable and indirect, but real, from Jupiter's gravitational influence on Earth's orbit to the evolution of the human brain. Now, let's come back to the moon, because there is one more gift it offers that is easy to overlook and deeply important. Earth's axial tilt, that 23.5-degree lean that gives us seasons, is not fixed. Without a large moon, computer simulations suggest that Earth's axial tilt would vary chaotically over millions of years, swinging perhaps between near zero and more than 80 degrees. A tilt of near zero would eliminate seasons almost entirely, creating a world of fierce equatorial heat and frigid ice-locked poles. A tilt of 80 degrees would mean that during summer, one pole would face the sun continuously for months, while the opposite hemisphere froze in total darkness, an extreme climate regime that would challenge the survival of complex life. The moon's gravitational stabilizing influence on Earth's axial tilt has kept that wobble within a relatively narrow range for billions of years. Seasons remain gentle enough for life to adapt to. Climates remain stable enough for ecosystems to persist. The moon, in other words, is not a passive passenger orbiting a living planet. It is, in a measurable and scientifically documented sense, one of the conditions that allowed that living planet to remain living. Its gravity steadies the Earth's wobble. Its tidal forces have shaped coastlines, influenced biological rhythms, and possibly played a role in the evolution of early life in tidal pool zones that were alternately submerged and exposed, creating environments where chemistry could concentrate, dry out, re-wet, and try again. There is something quietly moving about the moon's role in all of this. Most of us look up at the moon and feel something beauty mystery, a vague sense of connection to something older than ourselves. But the science tells us that feeling has a physical basis. The moon has genuinely been present through the entire story of life on Earth. Its gravity has been pulling on every ocean, stabilizing every season, nudging the planet's spin for 4 billion years. It was there when the first photosynthetic bacteria began releasing oxygen into the atmosphere. It was there when the first animals crawled onto land. It was there the night your earliest ancestors looked up and felt exactly what you feel now. The dance between Earth and Moon is old. It is slower now than it once was, and it will continue to slow the Moon, drifting outwards centimeter by centimeter until in some distant future the two bodies reach a final equilibrium. Earth's rotation perfectly synchronized with the Moon's orbit, each body always showing the same face to the other, locked in a permanent mutual gaze across space. But gravity, as patient as it is, does not only dance gently, it also reveals itself in ways that require a completely different framework to understand a framework that Newton never had, and that the world would have to wait until 1915 for a single extraordinary mind to provide. Because what we have described so far, orbits, tides, planetary formation, stellar birth, all of it follows Newton's equations beautifully. But there are places in the universe where Newton's framework quietly breaks down, where the familiar math stops working, where space and time themselves bend. And understanding those places requires us to meet at last the man who changed everything we thought we knew about what gravity actually is. In 1907, a 28-year-old man sitting at a desk in a patent office in Bern, Switzerland, had what he would later describe as the happiest thought of his life. He was not at that moment a famous scientist. He had published his special theory of relativity 2 years earlier, but it had not yet transformed the world of physics. He was still a civil servant, reviewing other people's inventions for a living, thinking about physics in whatever quiet moments the workday allowed. And the thought that came to him, sudden complete arriving, almost like something remembered rather than discovered, was this: a person falling freely through space feels no gravity at all. That sentence sounds simple. It may even sound obvious, but follow it carefully, because inside it is a revolution that would take Einstein 8 more years of the most difficult mathematical work of his life to fully articulate. And when he finally did in November 1915, it would change not just physics, but our understanding of what space-time and reality itself actually are. Let's begin with what Einstein noticed in that patent office. Imagine you are in an elevator and the cable snaps. You are in free fall, dropping toward the ground. In the brief seconds before the elevator hits the floor, if you let go of your keys, they don't fall to the floor of the elevator, they float beside you. Your feet don't press against the floor. Your body feels weightless. Every object in the elevator is falling at exactly the same rate. So, relative to each other and relative to the elevator walls, nothing moves. From inside that falling elevator, if you couldn't see outside, you would have no way to detect gravity at all. It would be as if gravity had simply switched off. Now, reverse the thought experiment. Imagine you are in a windowless room, in deep space, far from any planet or star, with no gravity whatsoever. A rocket engine fires beneath the room, accelerating it upward at exactly 9.8 meters per second, squared the same rate as Earth's gravitational acceleration. You stand on the floor, your feet press against it, you drop your keys, and they fall to the floor. You feel exactly what you feel standing in a room on Earth. From inside that room, with no way to see outside, you cannot tell whether you are sitting still on Earth's surface or accelerating through empty space. Gravity and acceleration feel identical. Einstein looked at this equivalence, which physicists had known about mathematically since Newton, but never taken seriously as a deep physical truth, and asked a question no one had asked before. What if gravity and acceleration are not just equivalent in their effects? What if they are in some fundamental sense the same thing? This is the equivalence principle, and it is the seed from which the general theory of relativity grows. But to understand where it leads, we need to think about what acceleration does to space and time. And for that, we need one more thought experiment. Imagine a beam of light entering your accelerating room through a small hole in one wall traveling horizontally. By the time the light crosses the room and hits the opposite wall, the room has accelerated upward slightly. So the light hits the wall slightly lower than where it entered. From inside the room, the beam of light has curved downward. It bent. Now, apply the equivalence principle if you cannot distinguish between acceleration and gravity. Then, in a room sitting still on Earth's surface, a beam of light must also bend downward under the influence of gravity. Light, which has no mass, which Newton's gravity should not affect, must be bent by gravity. Einstein predicted this in 1911, 4 years before he completed the full general theory. And he went further. If gravity bends light, and if light always travels in what we perceive as a straight line, then gravity must be bending space itself. The path of light is the straightest possible path through space, what mathematicians call a geodesic. If that path curves near a massive object, it is not because gravity is reaching out and tugging the light sideways. It is because the space through which the light is traveling is itself curved. Massive objects don't pull on things around them. They warp the geometry of the space around them, and everything moving through that warped space, light. Planets, comets, you simply follows the straightest path available. What we experience as the pull of gravity is the geometry of curved space-time, guiding us along those paths. The analogy most often used to explain this, and it's genuinely useful even if imperfect, is a stretched rubber sheet. Place a heavy ball in the center of the sheet, and it sinks, creating a depression, a curve in the flat surface. Now, roll a marble across the sheet. Instead of traveling in a straight line, it curves toward the depression, spiraling inward. The marble isn't being pulled by a force emanating from the heavy ball. It's following the curved surface of the sheet. Replace the rubber sheet with the fabric of space-time, replace the heavy ball with the sun, and replace the marble with a planet, and you have Einstein's picture of gravity, not a force, a geometry, not a pull, a curve. This is a conceptually staggering shift. For 200 years, gravity was a force invisible, instantaneous in Newton's original formulation, reaching across empty space like a kind of cosmic magnetism. Einstein replaced that picture with something geometrical, something woven into the structure of space and time themselves, something that has no separate existence from the fabric of the universe, but is, in a sense, that fabric expressing its own shape. The universe is not a stage on which gravity performs. The universe's shape is gravity. Now, beautiful ideas in physics must survive contact with experiment. And Einstein's general theory of relativity faced its first great empirical test, not in a laboratory, but during a solar eclipse on May 29, 1919, over the island of Príncipe, off the west coast of Africa, and in the town of Sobral in northern Brazil. The test was this. Einstein's theory predicted that light from distant stars passing close to the sun would be deflected by a specific calculable amount, twice the deflection that Newton's gravity would predict if you treated light as a particle with mass. During a total solar eclipse, when the moon blocks the sun's disk, it becomes possible to photograph stars whose light passes near the sun and compare their apparent positions to their known positions when the sun is not nearby. If the positions appear shifted, if the stars seem slightly displaced from where they should be, it means the sun's gravity has bent the light on its way to Earth. The amount of the shift would tell you which theory was right. The expedition was led by the British astronomer Arthur Eddington, who had championed Einstein's work in England during a time when anti-German sentiment following the First World War made it difficult for many British scientists to engage seriously with German physics. Eddington measured the deflection of starlight around the sun. The result matched Einstein's prediction, not Newton's Einstein's. When the results were announced at a joint meeting of the Royal Society and Royal Astronomical Society in London in November 1919, the president of the Royal Society declared it the greatest scientific achievement since Newton. The next day, newspapers around the world carried the story. Einstein became essentially overnight the most famous scientist on Earth. Here is a detail worth pausing on. Einstein had been so confident in his theory that when a student asked him in 1919 what he would have thought if the eclipse measurements had contradicted general relativity, he reportedly replied, "Then I would feel sorry for the dear Lord. The theory is correct." That degree of confidence, not arrogance, but the deep, hard-won certainty of a person who has followed an idea to its logical conclusion and found it internally coherent at every step, is one of the hallmarks of genuinely revolutionary science. Einstein wasn't gambling. He had followed the mathematics where it led and trusted what he found there. General relativity did not just predict the bending of light. It predicted that time itself runs at different rates depending on how deep you are in a gravitational field. The stronger the gravity, the slower time passes. This is not a metaphor. It is a measurable, verified, technologically consequential fact. The GPS satellites orbiting Earth experience slightly weaker gravity than clocks on the surface, which means their onboard clocks run very slightly faster, about 45 microseconds per day. Faster due to gravity partially offset by about 7 microseconds per day, slower due to their orbital velocity. If engineers did not account for this relativistic time difference and correct for it, GPS systems would accumulate errors of roughly 10 kilometers per day, rendering them useless for navigation. Every time you use GPS, every time your phone tells you where you are, it is running on a correction factor calculated from Einstein's general theory of relativity. Einstein's abstract geometrical theory of gravity is embedded in the infrastructure of modern life. Time runs slower at sea level than at the top of a mountain. Time runs slower at the base of a skyscraper than at its roof. Atomic clocks accurate enough to detect this difference have verified it directly. In 2010, physicists at the National Institute of Standards and Technology measured the difference in clock rates between two atomic clocks, placed at heights differing by just 1 foot. They could detect it. Gravity slows time not just near black holes or neutron stars, but right here in the room, where you are sitting at a rate that can be measured with sufficiently precise instruments. You age very slightly faster at the top of your head than at the bottom of your feet, by an amount too small to matter for any practical purpose. But the effect is real, and it is gravity bending not just space, but time. Does that feel strange to sit with for a moment? The idea that time is not fixed, not the same for everyone, not flowing at a single universal rate, but elastic, stretchable, shaped by the presence of mass. Newton's universe was a clockwork space, a fixed container, time, a steady river gravity, a force threading through it all. Einstein's universe is something softer, stranger, more intimate. Space and time are not the stage. They are actors in the story. And the most massive actor of all is gravity rewriting the geometry as it goes. The ripples that Einstein's equations predicted, gravitational waves, actual disturbances in the fabric of space-time, spreading outward from massive accelerating objects like ripples in a pond, were considered by many physicists to be real, but probably forever undetectable, too small to ever measure. Einstein himself doubted at various points in his life whether they could ever be observed. And yet, on September 14th, 2015, exactly 100 years after Einstein completed the general theory detectors at the LIGO Observatory in the United States, registered a signal lasting less than a second, a tiny distortion of spacetime smaller than 1,000th the diameter of a proton, passing through the Earth at the speed of light. It had been generated 3 billion years ago when two black holes, each more massive than 30 suns, spiraled together and merged in a catastrophic collision, sending out a burst of gravitational energy so enormous that it briefly outshone in gravitational wave power all the stars in the observable universe combined. The signal had traveled for 1.3 billion years and arrived at our detectors precisely when our technology had, for the first time in history, become sensitive enough to detect it. We heard the universe move. That signal, that brief chirp in the data, confirmed the last major untested prediction of general relativity. It opened an entirely new way of observing the cosmos, and it was in the most literal sense the sound of gravity speaking in its own language for the first time. A language Einstein had predicted a century earlier from a desk in a patent office following a thought about a person falling in an elevator. But if Einstein's relativity describes gravity at its most elegant as curved space-time, as gravitational waves, as time bending near mass, there exists a regime where even Einstein's framework reaches its edge, a place where the curvature of space-time becomes so extreme, so complete, so total, that the equations of general relativity themselves begin to break down, where nothing, not even light, can escape, where the familiar laws of physics arrive at their limit and stand at the edge of something we do not yet fully understand. That place has a name, and it is where our story goes next. There is a place in the universe where time stops, not slows, stops, where the escape velocity, the speed you would need to travel to break free from the gravitational pull, exceeds the speed of light, where the curvature of space-time becomes so extreme that all paths, every possible direction anything could move, curve inward, where the concept of outward ceases to exist. where matter is compressed to densities so extraordinary that our best physical theories arrive at their edge and go quiet. We call these places black holes. And for most of the 20th century, even the physicists who studied them weren't entirely sure they were real. The story of how black holes went from a theoretical curiosity to one of the most confirmed and studied objects in modern astrophysics is one of the great intellectual journeys in science, full of resistance, doubt, dramatic reversals, and one of the most visually stunning moments in the history of astronomy. And at the center of all of it is gravity pushed to its absolute limit. Let's begin not with Einstein, but with a quieter, less celebrated figure. In 1783, more than a century before Einstein was born, a British clergyman and amateur scientist named John Michell was thinking about Newton's theory of gravity and the nature of light. At the time, light was widely believed to consist of particles, tiny corpuscles of matter, as Newton had proposed. And if light was made of particles with mass, then gravity should affect it. Michell asked a question so ahead of its time that it would be largely forgotten for nearly 2 centuries. What if a star were massive enough and dense enough that its escape velocity exceeded the speed of light? The light particles from its surface would be launched upward, decelerate under the star's gravity, slow stop, and fall back. The star would be invisible, dark. Michell called them dark stars. He calculated correctly the basic relationship between a star's mass and the radius it would need to be compressed to in order for nothing to escape. That radius for any given mass is now known as the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who derived it mathematically from Einstein's equations in 1916, while serving on the Russian front during the First World War, dying of illness just months after sending his calculations to Einstein. Schwarzschild solved Einstein's field equations exactly for the case of a perfectly spherical, non-rotating mass, and his solution contains something disturbing. At a specific radius, what we now call the event horizon, the equations produced a singularity, a mathematical breakdown, a point where quantities became infinite and the familiar laws of physics stopped making predictions. Einstein himself was deeply uncomfortable with this result. He published a paper in 1939 arguing that in practice, real physical processes would always prevent matter from collapsing to such densities. Many physicists agreed. The mathematical object was real. The physical object they believed was probably not. That consensus began to crack in 1939, the same year Einstein published his skeptical paper, when 2 American physicists, Robert Oppenheimer and Hartland Snyder, published a calculation showing that a sufficiently massive star at the end of its life could in fact collapse past the Schwarzschild radius. Not hypothetically. Actually, the collapse they showed was physically possible. The mathematics didn't just permit it, it demanded it under the right conditions, and there was nothing in the laws of physics that would stop it. So, let's follow what actually happens when a massive star dies, because this is where gravity's creative power turns for the first time into something that can only be called destructive. A star spends its entire life in the balance we described in Part 3, gravity pulling inward, fusion energy pushing outward. But fusion is not infinite. Stars have a finite amount of fuel. Our sun will burn hydrogen for roughly 10 billion years, total, then briefly fuse helium in its outer layers, swell into a red giant, shed those outer layers into space as a planetary nebula, and leave behind a dense core called a white dwarf, an object the size of Earth. But with the mass of the sun held up not by fusion, but by a quantum mechanical effect called electron degeneracy pressure, which prevents electrons from being compressed into the same quantum state. No more fusion. Just a slowly cooling ember fading over billions of years into darkness. But for stars significantly more massive than our sun, roughly 8 to 20 times the sun's mass or more, the ending is different. When the core's nuclear fuel is exhausted, the balance collapses. There is no more outward pressure to oppose gravity. The core implodes in a fraction of a second, less than a quarter of a second for the innermost layers compressing a mass greater than the Sun into a ball roughly 12 miles across. The implosion releases more energy in that fraction of a second than the Sun will emit in its entire 10 billion year lifetime. The outer layers of the star falling inward hit the suddenly rigid core and rebound in a catastrophic explosion, a supernova. Briefly, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The collapsed core left behind, if its mass falls below a certain threshold, becomes a neutron star, a city-sized sphere of matter so dense that a teaspoon of it would weigh roughly 1 billion tons, its electrons and protons crushed together into neutrons by the sheer force of gravitational collapse. But if the collapsing core is massive enough, if its mass exceeds roughly 2 to 3 times the mass of our Sun, even neutron degeneracy pressure cannot resist gravity. Nothing can. The core continues collapsing past the neutron star stage, past any known physical barrier, contracting toward a mathematical point of infinite density called a singularity, surrounded by an event horizon from which nothing can return. A black hole is born. Now here is perhaps the most persistently misunderstood thing about black holes, and it is worth addressing directly because it shapes everything else about how we think about them. Black holes are not cosmic vacuum cleaners. They do not suck in everything around them. They do not reach out across space and pull in distant matter. If our Sun were somehow magically replaced right now with a black hole of exactly the same mass, a horrifying thought. For other reasons, Earth would not spiral inward. It would continue orbiting exactly as it does now, at the same distance, at the same speed, in the same path. The gravitational field outside a black hole of a given mass is identical to the gravitational field of a non-collapsed object of the same mass at the same distance. What makes a black hole dangerous, what makes its event horizon inescapable, is not that its gravity is stronger at a distance, but that if you get too close, you cross a threshold from which no path leads outward. The event horizon is not a physical surface. It is a point of no return. Cross it and every possible future you have leads inward. What lies inside the event horizon? Honestly, and this is one of the places where physics speaks most carefully and most humbly, we don't fully know. General relativity predicts a singularity at the center, a point of infinite density. But most physicists believe that the singularity is not a real physical feature of the universe, but rather a signal that general relativity itself is breaking down, that at those extreme densities and curvatures, we need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity that we do not yet have. The singularity in this view is where our current best description of reality reaches its edge and honestly admits it cannot see further. For decades, black holes remained purely theoretical. There was strong mathematical reason to believe they existed, but no direct observational evidence. That began to change in the 1960s and 1970s as astronomers using radio telescopes and X-ray observatories began finding objects in the sky that could only be explained by the presence of extremely compact, extremely massive bodies, X-ray binary systems, where a normal star appeared to be orbiting an invisible companion with material streaming from the visible star onto the invisible one, and heating to millions of degrees, producing bright X-ray emission, provided the first strong indirect evidence. The most compelling early candidate was Cygnus X1, discovered in 1964, whose invisible companion was calculated to be far too massive to be a neutron star. The debate over whether Cygnus X1 was truly a black hole was famously the subject of a bet between Stephen Hawking and Kip Thorne in 1974, Hawking betting against as a kind of insurance policy, Thorne betting in favor. By 1990, the evidence had become so overwhelming that Hawking conceded the bet. Then came the supermassive black holes, and here the scale becomes almost ungraspable. At the centers of most large galaxies, including our own Milky Way, there sit black holes, millions or billions of times more massive than the Sun. The black hole at the center of the Milky Way, known as Sagittarius, A star, has a mass of roughly 4 million solar masses compressed into a region smaller than the distance between Earth and the Sun. In 2022, the Event Horizon Telescope Collaboration, a global network of radio telescopes linked together to form an effective telescope the size of the Earth, published the first direct image of Sagittarius. A star, a glowing ring of hot gas swirling around a dark central shadow, exactly matching the predictions of general relativity. We photographed the mouth of gravity's deepest known expression. We saw the shadow of something from which no light can escape outlined by the light that came just close enough to be bent into a ring instead of captured. And here is something that quietly reframes the entire history of the Milky Way. The supermassive black hole at its center is not a passive resident. Researchers studying the orbits of stars near Sagittarius, A-star stars that complete full orbits in as little as 16 years around an invisible point, have tracked these stellar orbits for decades. The precision of those measurements combined with the velocities involved have confirmed not just the mass of the central black hole, but have provided some of the most precise tests of general relativity ever conducted. Tests performed not in a laboratory, but at the center of our own galaxy, around an object 4 million times the mass of the Sun. There is a concept in the physics of black holes called Hawking radiation, proposed by Stephen Hawking in 1974, which suggests that black holes are not entirely black, that quantum mechanical effects near the event horizon cause them to very slowly emit thermal radiation, losing mass over immense timescales. A black hole the mass of our Sun would take approximately 10 to the power of 67 years to evaporate in this way, a number so vast it makes the current age of the universe at 13. 8 billion years look like a rounding error. Hawking radiation has never been directly detected. The effect is far too faint to measure with current technology for any known black hole, but its theoretical basis is widely accepted, and it points towards something profound. Even the most extreme gravitational objects in the universe are in the very longest of long runs temporary. Gravity builds, gravity binds, and given sufficient time, even gravity's most absolute creation slowly unravels. Have you ever looked at the night sky and tried to find the center of the Milky Way? On a very clear night far from city lights, you can see a dense band of stars and dust stretching across the sky. The center of the galaxy lies in the direction of the constellation Sagittarius low in the southern sky during northern hemisphere summers. You cannot see Sagittarius A star directly. Too much gas and dust lies between us and it. But it is there 4 million solar masses of compressed space-time, surrounded by stars orbiting at thousands of miles per second, bending light, warping time, anchoring the slow rotation of hundreds of billions of stars, including our own Sun in its 230 million-year journey around the galactic center. The gravity of that unseen object has shaped the structure of the Milky Way for billions of years. It shaped the conditions under which the Sun formed. In the most indirect but real sense, it is part of why you are here. Black holes sit at one extreme of gravity's range, the place where its effects become absolute, where space and time themselves are so distorted that they lose their familiar character entirely. But gravity's story does not end at the edge of a black hole. It continues outward to the largest scales the universe contains, to the question of how all the matter in the cosmos is arranged and why it is arranged that way, and to a discovery made in 1998 that shocked the entire physics community because it suggested that gravity, for all its patience and power, may ultimately lose the greatest contest it has ever entered. In 1998, 2 independent teams of astronomers set out to do something that seemed on the surface fairly straightforward. They wanted to measure how fast the universe's expansion was slowing down. Not whether it was slowing, that seemed certain. Everyone expected it to be slowing. Gravity pulls matter together. The universe had been expanding since the Big Bang. Naturally, the collective gravity of all the matter in the cosmos must be acting as a brake on that expansion, gradually decelerating it over time. The only real question was how much. Was there enough matter to eventually halt the expansion entirely and pull everything back together? Or would the universe expand forever, but ever more slowly, cooling and thinning as it went? These were the options on the table. Both teams were simply trying to measure which one was correct. What they found instead was something neither team expected, something that neither group initially believed, something that both teams spent months checking and rechecking before they were willing to publish. The expansion of the universe was not slowing down. It was speeding up. Galaxies were not decelerating under gravity's patient pull. They were accelerating away from each other faster and faster, driven by something no one had detected, no one had predicted with any confidence, and no one to this day truly understands. The discovery earned its lead researchers the Nobel Prize in Physics in 2011. And it fundamentally changed our picture of gravity's role in the ultimate fate of everything. To understand what that discovery means and why it shook physics so deeply, we need to first understand what the universe looked like before 1998 and what cosmologists thought they knew. After the Big Bang, approximately 13.8 billion years ago, the universe was unimaginably hot, dense, and uniform. A seething plasma of energy and matter, expanding in all directions simultaneously. Not expanding into space because space itself was what was expanding. The Big Bang was not an explosion at a point in an existing void. It was the beginning of space-time and matter together, and the expansion is the stretching of space itself, carrying galaxies along with it, the way dots on a balloon move apart as the balloon inflates. For the first several 100,000 years, the universe was so hot and dense that atoms couldn't even form protons, and electrons existed separately in a plasma so energetic that any atom that tried to assemble was immediately torn apart by radiation. Only when the universe had expanded and cooled enough did atoms form, and only then did light travel freely for the first time. That first light, the cosmic microwave background radiation, still fills the entire universe today as a faint uniform glow of microwave radiation detectable in every direction. With the right instruments, a ghostly afterimage of the moment the universe became transparent. As the universe expanded and cooled, gravity began its work. Tiny variations in density quantum fluctuations from the earliest moment stretched to cosmic scale by rapid early expansion provided the seeds. Regions slightly denser than average pulled in surrounding matter. Over hundreds of millions of years, those regions grew denser, still eventually collapsing into the first stars and the first galaxies. Gravity organized the universe's matter into the vast cosmic web we observe today. A three-dimensional network of filaments, sheets and nodes of galaxies surrounding enormous voids, nearly empty of matter, stretching across hundreds of millions of light years. Every galaxy cluster, every supercluster, every cosmic filament is a monument to gravity's patient organizing work over billions of years. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a massive concentration of galaxies spanning roughly 10 billion light-years, discovered in 2013. It is so large that light takes 10 billion years to cross it. For comparison, the observable universe is only 93 billion light-years across, a single structure assembled by gravity over billions of years, spanning more than 10% of the entire observable universe. The scale is in an honest sense beyond what the human mind can truly hold. We can say the numbers. We cannot feel them. Now, back to 1998 and the accelerating universe. To make sense of what those two teams discovered, we need to understand what they were actually measuring. Both groups were studying a particular type of exploding star, a Type 1A supernova, that has a remarkable property. Because of the specific physics of how they form and explode, all Type 1A supernova release almost exactly the same total amount of energy. They are, in astronomical terminology standard, candles, objects of known intrinsic brightness. By comparing how bright a distant Type 1 A supernova appears to us with how bright it should be based on its intrinsic luminosity. Astronomers can calculate its precise distance. And by measuring the redshift of its light, how much the wavelength has been stretched by the expansion of space during the light's journey to us. They can measure how fast the universe was expanding at the time the supernova exploded. Do this for enough supernovae at enough distances, spanning enough of cosmic history, and you can reconstruct the entire history of the universe's expansion rate. That is what both teams did. And what the data showed was that distant supernovae from the early universe were slightly fainter than they should have been if the expansion were decelerating at the expected rate. The universe at that era was expanding more slowly than it is now. Something has been making the expansion accelerate over the past several billion years. Physicists gave that something a name: dark energy, and it currently accounts for roughly 68% of the total energy content of the universe, with dark matter making up about 27% and all the ordinary matter, every star, planet, gas cloud, and living creature, comprising only about 5%. Everything we can see, touch, or detect with any instrument represents approximately 1/20th of what actually exists. Dark energy is not dark because it absorbs light. It is dark because it is invisible to every instrument we have, detectable only through its gravitational effect, or rather its anti-gravitational effect, on the expansion of space. What dark energy actually is remains one of the deepest unsolved problems in all of physics. The leading hypothesis, the simplest mathematical description that fits the data, is that it is a property of space itself. Empty space on this view has a small but non-zero energy density, sometimes called the cosmological constant, a term Einstein actually introduced into his equations in 1917 for entirely different reasons, and later famously called his greatest blunder. He added it to make the universe static, to balance gravity, and prevent the universe from expanding or contracting. When Edwin Hubble confirmed in 1929 that the universe was expanding, Einstein abandoned the cosmological constant. But the universe, it seems, did not get the memo. The constant appears to be real, just not for the reason Einstein imagined. The competition between gravity and dark energy is not a competition taking place at any single location. It is a competition of scales. At small scales within galaxies and galaxy clusters, gravity wins decisively. The Milky Way, the Andromeda Galaxy, and the other members of our local group are gravitationally bound to each other, and no amount of dark energy will tear them apart. The Andromeda Galaxy is actually approaching the Milky Way at roughly 70 miles per second, and will merge with it in approximately 4.5 billion years, a colossal gravitational embrace that will reshape both galaxies over hundreds of millions of years into a single giant elliptical galaxy, sometimes informally called Milkomeda. Dark energy plays no role in this. At the scale of galaxy clusters, gravity still holds. But at larger and larger scales between superclusters, across the voids, across the full breadth of the cosmic web, dark energy dominates. And as the universe continues to expand, as those vast voids grow wider, the regions where gravity can win grow more isolated. Galaxy clusters drift apart. Superclusters become unreachable. The observable universe over an incomprehensibly long future will thin and empty. This brings us to the question of cosmic destiny, and to three scenarios that physicists have considered as possible endings for the universe. Each one a different answer to the question of how the contest between gravity and dark energy ultimately resolves. The first scenario is called the Big Freeze, sometimes also called the heat death of the universe. This is the fate that current data most strongly suggests. Dark energy continues driving the expansion of space. Galaxies drift further apart over hundreds of billions of years. Stars exhaust their fuel and fade one by one. The last stars burn out perhaps 100 trillion years from now. Black holes slowly evaporate through Hawking radiation, over time scales measured in numbers too large to comfortably write. The universe approaches a state of maximum entropy, perfectly uniform, perfectly cold, with no gradients of temperature or energy to drive any further process. Not a violent end, a slow, quiet dispersal. The universe doesn't explode. It simply runs down like a clock that was never rewound. Gravity built everything. Time and entropy unravel it. The second scenario, the Big Rip requires dark energy to be not a fixed cosmological constant, but a quantity that grows over time. If dark energy increases as the universe expands, then eventually it would become strong enough to overwhelm not just the gravity between galaxy clusters, but within galaxies, then within solar systems, then between planets and moons, then between molecules, then between atoms, and finally, in the last fraction of a second, between the subatomic particles themselves. Everything would be torn apart simultaneously everywhere, in a sudden final expansion of infinite violence. Current data does not favor this scenario, but it has not been ruled out entirely. The nature of dark energy is still uncertain enough that the Big Rip remains a possibility physicists take seriously. The third scenario, the Big Crunch requires dark energy to eventually weaken or reverse, allowing gravity to ultimately win. If that happened, the expansion would decelerate, halt, and reverse. Galaxies would begin approaching each other, the cosmic web would contract, galaxy clusters would merge, then galaxies, then stars would grow closer together, the sky filling with a blaze of light as the temperature of the universe rose until everything collapsed back together into a state of unimaginable density, the mirror image of the Big Bang. Current cosmological evidence strongly disfavors this outcome, but the honest answer is that we do not understand dark energy well enough to confidently rule it out forever. Here is something worth sitting with in the quiet of this moment. These three scenarios, freeze, rip, crunch, are not science fiction. They are the genuine mathematically grounded predictions of our best current theories, informed by the best data humanity has ever collected about the structure and history of the cosmos. We live in a universe whose ultimate fate is genuinely uncertain, not because the physics is sloppy, but because the physics is honest. There is still something dark energy that we don't understand. And in science, when you don't understand something, you say so. The most common misunderstanding about this cosmic contest is the idea that gravity is losing, that dark energy is winning, and the universe is therefore in some sense doomed. But this framing misses something important. Gravity has already done the extraordinary thing. It built the stars. It organized the galaxies. It created the conditions for planets and for life and for consciousness. It gave the universe structure and complexity and meaning, in the sense that meaning is possible at all in a physical universe. Whatever dark energy eventually does to the large-scale geometry of the cosmos, it cannot undo what gravity has already accomplished. The sun will burn for another 5 billion years. The Milky Way will persist for hundreds of billions more. The universe is not running out of time on any scale that touches anything we love. We are early. We are in cosmic terms barely begun. Do you ever feel the weight of time when you look at the night sky? That sense of scale, of how small this moment is, against the backdrop of billions of years stretching in both directions. There is something in that feeling worth honoring, not dread wonder. We exist at a peculiar privileged temporary moment in cosmic history, when the universe is neither too young nor too old, when stars are still burning, when galaxies are still close enough to study, when the cosmic microwave background is still detectable, when the evidence of the universe's origin and history is still readable in the sky if you know how to look. The physicist Brian Greene has noted that in the very far future, 100 billion years from now, when the expansion of the universe has carried all other galaxies beyond the observable horizon, any civilization that exists in the Milky Way will look out at a sky nearly empty of other galaxies. They will have no way to know that the universe was once filled with them. They will have no way to deduce the Big Bang. The evidence will be gone. We happen to live at the one era in cosmic history when that evidence still exists, still visible, still teaching us what happened and what is happening. That is not an accident to take lightly. That is a gift of timing, delivered by the same expansion that will eventually take it away. The contest between gravity and dark energy plays out across scales and time scales that dwarf everything human. But here in this last stretch of our journey tonight, we're going to pull the lens all the way back from cosmic fate to something quieter and closer. Because after everything we've traveled through, from falling object to forming stars, from orbiting moons to bending space-time, from black holes to the destiny of the universe, there is one more question worth asking. The most personal one of all. What does any of this mean for us? What does gravity in all its forms tell us about what it means to be here alive on this particular world, at this particular moment in time? We have traveled a long way tonight, from a falling leaf to the death of stars, from Newton's farmhouse to Einstein's patent office, from the moon's quiet drift to the edge of black holes, from the birth of planets to the ultimate fate of the cosmos. And now, in this final stretch of our journey, I want to do something different. I want to bring all of that, the distances, the time scales, the physics, back to something small enough to hold. Back to you. Back to this moment. Back to the question that science at its most honest and most human always eventually arrives at: what does any of this mean for the life being lived right now on this small, gravity-held world? This is not a question physics can answer alone, but physics can illuminate it in ways that nothing else quite can. Let's begin with a number: 9.8 meters per second squared. The acceleration due to gravity at Earth's surface. It is one of the most measured, most verified, most precisely known quantities in all of science. Drop any object near sea level in the absence of air resistance, and after 1 second, it is moving at 9.8 meters per second. After 2 seconds, 19.6. After 329.4. The relationship is exact, universal, and has been confirmed by experiments ranging from Galileo's bronze balls on inclined planes in the 1590s to modern atom interferometry, a technique that uses quantum mechanical properties of atoms to measure gravitational acceleration to better than 1 part in 10 billion. We know this number with extraordinary precision. And yet, here's the quietly beautiful thing: we still do not have a complete theory of why it is what it is. We can measure it. We can describe it. The deepest reason for its exact value remains in some fundamental sense an open question. Science knows how to be precise about what it measures while remaining humble about what it doesn't yet understand. That combination, precision and humility, might be the most important lesson gravity has ever offered. Now let's talk about weight. Not in the bathroom scale sense, but in the cosmic sense. Your weight the force gravity exerts on your body is not a fixed property of you. It is a relationship between you and whatever massive body you happen to be standing near. On the moon, you would weigh about 1/6 of what you weigh on Earth, the same mass, far less gravitational pull. On Mars, roughly 38% of your Earth weight. On Jupiter's cloud tops, if you could somehow stand there, you would weigh about 5 times what you weigh now, every step. An enormous effort, your heart working hard to push blood through arteries, suddenly carrying far more effective weight. On a neutron star, your weight would be approximately 100 billion times what it is on Earth. The atoms of your body would not survive the tidal forces for a fraction of a second. You would be spread across the neutron star's surface in a layer thinner than an atomic nucleus. This is not morbid, it is clarifying. What you call your weight is not about you. It is about where you are. Gravity is always relational, always contextual, always a conversation between objects rather than a property of any single one. There is a small but striking experiment that researchers at the National Institute of Standards and Technology conducted in 2010. We touched on it briefly in part 6, but its full implication is worth returning to now. They placed 2 of the world's most precise atomic clocks so accurate they would neither gain nor lose a second in 300 million years, at heights differing by just 33 centimeters. Not 33 meters, 33 centimeters. roughly the height of this sentence to the bottom of the page. And they measured a difference in clock rates. The lower clock ran measurably slower because it sat deeper in Earth's gravitational field. Time itself, at the scale of a human body, runs at different rates from head to toe. Not by enough to matter for any daily purpose, the difference is on the order of 10 to the power of negative 16 seconds per second. But the principle is real, verified, and physically consequential. Gravity does not just shape the universe at cosmic scales. It reaches into the most intimate details of physical existence. It touches the passage of time inside the space your own body occupies. Here is something that has always moved me about the history of gravitational science, and I want to share it directly. Every major advance in our understanding of gravity, from Galileo's inclined planes to Newton's Principia, to Einstein's field equations, to the detection of gravitational waves in 2015, came not from someone who had more resources than everyone else, but from someone who looked at something familiar and refused to accept the conventional explanation. Galileo questioned Aristotle not because he had better instruments, his water clock was crude by any standard, but because he actually tested the claim instead of accepting it. Newton connected a falling apple to the orbiting moon, not because it was an obvious connection, but because he was willing to ask whether an invisible force could truly reach across 240,000 miles of empty space. Einstein imagined a person in a falling elevator and followed that thought for 8 years through mathematics so difficult, it required him to essentially learn a new branch of geometry. The LIGO team built detectors capable of measuring a distance 1,000th the diameter of a proton, not because anyone told them they would certainly succeed, but because the physics said the signal should be there, and they were patient enough to build the instrument to find it. Every one of these advances required the same thing, a willingness to take a simple observation seriously enough to follow it wherever it led, regardless of how strange the destination turned out to be. That is not a lesson only for physicists. It is a description of what careful, honest thinking looks like in any domain, and gravity has been teaching it to us patiently for as long as we have been paying attention. Let's talk about what gravity does to the human body over a lifetime, because this is one of the places where the physics becomes deeply personally immediate. Your spine compresses under gravity every day. During the hours you are upright, the cartilage discs between your vertebrae are squeezed slightly by the weight of your body above them. When you lie down to sleep, those discs rehydrate and expand. You are measurably taller in the morning than in the evening, by as much as 1 to 2 centimeters. Astronauts returning from long missions on the International Space Station are sometimes several centimeters taller than when they launched, because their spines have expanded in the absence of gravitational compression. Within weeks of returning to Earth, they return to their pre-flight height. Your height, in a very real sense, is a daily negotiation with gravity. Your cardiovascular system was designed around gravity. The heart pumps blood upward against gravity to the brain, and downward with gravity to the feet. And the venous system in your legs contains one-way valves, specifically to prevent blood from pooling in your lower extremities under gravitational pull. When you stand up quickly and feel momentarily dizzy, that is your cardiovascular system briefly failing to compensate fast enough for the gravitational demand on blood pressure. When you lie down and feel your body relax completely, part of what you are feeling is your heart's workload decreasing, the demand of pumping against gravity partially relieved. Sleep, in a purely physiological sense, is partly a gravitational rest. Your body exhales gravity for a few hours each night and rebuilds itself for the next day's negotiation. And then there is bone. Human bone is a living tissue constantly remodeling itself in response to mechanical stress, the stress imposed primarily by gravity and muscular force. Bones grow denser where they bear weight regularly and thinner where they don't. This is why weight-bearing exercise, walking, running, resistance training, is the most effective known method of maintaining bone density as we age. It is also why extended spaceflight causes significant bone loss without gravity's constant demand. The skeleton gradually concludes at a cellular level, that it no longer needs to be as strong. Astronaut Scott Kelly, who spent 340 consecutive days on the International Space Station in 2015 and 2016, lost approximately 14% of his bone density and weight-bearing bones during the mission, recovered to near normal after extensive rehabilitation on Earth. But the process required months of deliberate work. Your skeleton is not a passive structure. It is a living archive of how much gravity you have asked it to carry. Every bone in your body is a record of where you have stood, how long you stood there, and how hard the Earth has been pulling you down. Now, let's zoom back out one final time to the very largest scale, because there is a perspective on gravity that only becomes visible when you hold all of it together at once. The collapsing molecular cloud, the igniting star, the accreting disk, the growing planets, the stabilizing moon, the curved space-time, the tidal rhythms, the bone and the heartbeat and the morning height. All of it, every single piece of this story, is one continuous process. There is no boundary where the cosmic gravity ends and the personal gravity begins. The same mathematics that describes the orbit of a planet describes the arc of a thrown ball. The same force that collapses a nebula into a star holds the blood in your vessels as you stand. The same curvature of space-time that bends light around a black hole also varies slightly by an amount too small to notice, but real enough to measure, bends the path of a photon, leaving a lamp in the room where you sit. Gravity does not operate at two levels, the cosmic and the human. It operates at one level continuously from the smallest measurable scale to the largest structure in the observable universe. What changes is only the amount of mass involved and therefore the magnitude of the effect. The physics is the same. Newton's equation, Einstein's field equations, one framework applied everywhere without exception, without preference, without awareness of the distinction between a galaxy and a grain of sand. There is something in that universality, something in the fact that the force holding you to the Earth is the same force that built the sun, that I find quietly and genuinely one of the most moving facts in all of science. Not because it makes us small, because it makes us continuous. You are not separate from the cosmos and then subject to its forces. You are part of the same gravitational story that has been unfolding for 13.8 billion years. The hydrogen atoms in your body were present in the early universe before any star existed. They were gathered by gravity into a molecular cloud, compressed into a star, fused into heavier elements in that star's core, scattered into space. By that star's death, swept up into the disk that formed the solar system, accreted into the Earth, cycled through oceans and atmosphere and geology for billions of years, incorporated into living cells, passed through generations of organisms, and arrived by an improbable and unbroken chain of gravitational and chemical and biological events in the body you inhabit right now. You did not fall into this universe. You grew out of it. Gravity grew you out of it, patiently, over an almost incomprehensible span of time. Does that change anything about how this moment feels? Does it make the weight of your body, the literal physical pressure of the Earth pulling you down, feel any different to know that the same force is also right now, building new stars in the Orion Nebula, holding the moon in its orbit, bending light around a black hole 4 million times the mass of the sun, at the center of our galaxy, and slowly over billions of years deciding the fate of the cosmos? It should maybe, not in a way that overwhelms, in a way that anchors. You are heavy because you have mass. You have mass because matter exists. Matter exists because gravity gathered it into stars that forged it into elements. The weight you feel is not a burden imposed on you by an indifferent universe. It is your connection to it. The most constant, most ancient, most universal relationship in the history of everything. I want to leave you with one final image. On July 20th, 1969, Neil Armstrong stepped off the last rung of the Eagle lander's ladder and placed his left foot on the surface of the moon. In that moment, his weight was approximately 1/6 of what it would have been on Earth. The gravity holding him to the lunar surface was the same gravity that had 4, 5 billion years earlier, gathered the debris from a catastrophic collision between the young Earth and the body we call Theia, coalesced it into the moon, and set it in the orbit that had been slowly drifting outward ever since. The moon that Armstrong stood on had been built by the same force that was now holding him to it. And the Earth hanging in the black sky above him, the pale blue arc he could cover with his thumb, was being held in its orbit by the same gravity that held him on the surface below. One force, one story, three expressions of the same patient, invisible, universal pull. Armstrong later said that standing on the moon and looking back at the Earth was a profoundly humbling experience, that the Earth looked small, fragile, and impossibly beautiful against the blackness of space. Gravity had given him that perspective. Gravity had built the rocket that carried him there, every combustion chamber, every structural beam calculated against the force that the rocket needed to overcome. Gravity had built the moon he stood on and the Earth he was looking at, and gravity would bring him home. We began tonight with a falling leaf, with the simple, unremarkable, endlessly repeated fact of things being drawn toward the ground. And we have followed that fact, that quiet, persistent, patient fact, all the way to the edge of the universe, to the nature of time, to the origin of everything you were made of, and back again to the ground beneath your feet. Gravity is not just a force in the equations. It is the thread that runs through the entire story of the cosmos, the architect of stars and planets, the sculptor of moons and mountain ranges, the keeper of orbits and the shaper of tides, the bender of light and the slow hand of cosmic fate. And the thing that holds you right now, in this moment, to the only home in the universe we know has ever harbored life. Thank you for traveling this far tonight. Thank you for staying with these ideas through all their strangeness and beauty and scale. Thank you for letting science be for a few hours not a subject to study, but a story to rest inside. There is something remarkable about the fact that the same force pulling you towards sleep right now is the same force that built the stars shining outside your window. Let that thought settle gently as your eyes grow heavy. You are held. You have always been held. By a force older than the sun, wider than the galaxy, and patient beyond any measure of time we have words for. Sleep well. Dream of deep space and quiet stars and the slow, steady pull of everything toward everything else. The universe will still be here when you wake. Gravity will make sure of it. And when you're ready for the next quiet journey, when the next night comes, and the world needs to be a little wider and a little more wonderful, we'll be here. The next story is already waiting, and I have a feeling it's going to take us somewhere you've never quite been before.